to talk about special right triangles, this time another one. We just wrapped up looking at the 30, 60, 90 right triangle, and it has these relationships. The shortest length across from the 30 has a length of x, hypotenuse is 2x, and then the middle length across from the 60 is x times the square root of 3. We will use another triangle this time. It's called the 45, 45, 90. It's a special isosceles triangle. But before I get to that, I want to see how we did this. How we did this is I started with an isosceles equilateral triangle. We broke it up, then we used the Pythagorean theorem. We're going to sort of do that again today with the 45, 45, 90. So, however, this time here, my triangle is going to look something like that, where this is 45 degrees, and this is 90. Also with this, you'll see me frequently write like this. These hash marks mean they're the same length. If they're the same length of an isosceles, these base angles must be the same. So, if these sides are the same length, let's figure out what this length is up here. Okay, so let's go ahead and use the same one we did last time. Let's call this 6 inches. And we're going to use Pythagorean theorem. And we're going to say a squared plus b squared equals c squared. We could call this a, call this b, call this c. So we're going to say 6 squared plus 6 squared equals c squared. Go ahead and add those up. We have 36 plus 36 equals c squared. Okay. Let's go ahead and add up 36. How about I be lazy? I'm going to be lazy. I'm going to say 2 times 36 equals c squared. That keeps me from having to actually add the numbers. You'll see why. It's actually a trick I'm doing here. To get rid of the square, I need to do the inverse, which is the square root, which is that. Okay. So, let's move this up to here, and we'll say 2 times 36 square root equals c squared. I got a square root also. Square and the square root inverses, they cancel. And we have 2 times 36 square root equals c. Almost there. 36 is a perfect square. So 6 times 6 equals 36. So this 36 can come out of the square root as the non-perfect square is 6. Then I end up with 6 root 2 equals c. So I can go back up to here and say this one here is 6 times the square root of 2. Now I want you to take a look. My side lengths are 6. This guy's 6 times the square root of 2. Now is this just unique for my one triangle with 6 inches on the sides? Or can I scale this down? So I'm going to try a different approach from last time. I'm going to go back to my little triangle here. Give myself some more space. 6, 6, 6 root 2. What if I scale this and I'm going to multiply it by 1 over 6. So I'm going to have a triangle that's a lot smaller, but we'll draw it that size. Okay, a little smaller. So what is 6 times 1 over 6? Okay, those are my 3 sides. Let's see, 6 times 1 over 6. This would be 1, 1. And over here would be 1 root 6. Not sure you can actually see that. Let me draw it a little bigger. 1. So that would be 1 times the square root of 2. I think I just said that wrong a minute ago. It's kind of confusing. It's a little bit small. I wanted to show you the relationship here. If I scale this down, so it's a side length of 1, so instead of 6 root 2, if I divide it all by 6 or multiply by 1 over 6, I get 1 root 2. And that is what we're seeing here. Let me clear this up a little bit. This is your second special right triangle. So we have a 45, 45, 90 special right triangle, where my side lengths are x, x, x times the square root of 2. These two special right triangles will get you through quite a bit. Again, 30, 60, 90 is x, 2x, x root 3. 45, 45, 90 is x, x, x times the square root of 2.